Great. I think we can go ahead and get started. So today we have Nicole Lewis here to tell us about searching for the baryon number carrier. Nicole started with her PhD at the University of Michigan, working with Christine Adalo on proton structure at Phoenix. She then did a postdoc at BNL working on STAR, looking at photonuclear type things, which she'll talk to you about today. And now is at Rice, also working on photonuclear studies, now on CMS. So Nicole, take it away.
Hey, everyone. Thank you so much for the opportunity to give this talk. So we're going to start, hopefully a little simply, with what is a baryon and what is its number carrier. So a baryon, put simply, is a bound state of 3 valence quarks that all come together as one. And a weird quirk of our universe is that baryon number, so the total number of baryons minus the number of antibaryons, is strictly conserved. The baryon number of the universe currently is the same baryon number as it was shortly after the Big Bang. If you open up a particle physics textbook, it will tell you that the baryon number is split evenly between the 3 valence quarks. There is also an alternative model. This is called a junction. So this is this Y-shaped configuration of very low momentum gluons, which is linked to all 3 of the valence quarks. It comes together at one point, or a junction. In this model, it's the junction that carries the baryon number. But neither of these scenarios has been experimentally verified. Trigger. So closely related to this is the concept of baryon stopping. So this is where we measure more baryons than antibaryons. Here we're looking at data from a gold-gold collision, and you might be thinking, well, we started with more baryons, we should probably end with more baryons than antibaryons. But so here we're looking at protons in red and then antiprotons in blue. And you can see we have a very clear excess, even perpendicular to the beamline. This baryon stopping is also called baryon number transport when you are trying to sound more fancy. We've seen that this continues into heavier baryons, not just protons, but omegas and lambdas and all types of heavier things. Often we measure this net baryon yield with what we call the inclusive net proton yield. So here, these are inclusive protons. They include all of the stuff that came from decays of heavier baryons. We're not correcting for that or removing that. And this is a good proxy for net baryon number measured with particles that we know how to measure, protons and antiprotons. So we can look at this net proton yield as a function of collision energy. So here I'm measuring it as a function of, always great to get a spam call in the middle of your talk. Here I'm measuring it as a function of beam energy, or the rapidity, the speed of the beam. And you can see that this baryon stopping decreases with beam energy. That kind of makes sense. The faster my baryons are going initially, the harder they are to stop. What is striking about this plot is there's this pretty clear exponential dependence on this quantity. So this is the change in rapidity from the beam to where we're measuring it. And this is something that cannot be explained in the valence quark picture. So we can also look at this net proton yield as a function of centrality. And to explain what I'm talking about, I think we should take a couple of steps back. So I'm talking about heavy ion collisions. I will just quickly, when I say heavy ion collisions in my field, I'm talking about the nucleus of a large atom. I say that because I've given this seminar one time, and at the very, very end, someone asked me what a heavy ion is. So to avoid any confusion, I will say it now. So these ions are so large that it actually matters how they collide with each other. We have this concept of impact parameter, which is related to this overlap region. So we have some of these nucleons, these protons and neutrons, which do not participate in the collision. They're called spectators. They continue along the beamline. And then we have these participants, where if the energy density is high enough, they will collide and sort of melt and create this quark-gluon soup that we call the quark-gluon plasma. It's a different phase of matter. A lot of what is being done at the relativistic heavy ion collider is trying to map out this phase of matter and how it changes with different parameters. So something that is still under investigation and a very fruitful avenue of study, which a lot of people in this room are working on. And the concept of centrality is how overlapping these collisions are happening. That wasn't a sentence, but just go with it. That is related to multiplicity, which is a fancy way of saying the number of things in my collision. At star, we have this part of our detector we're very confident in, that we can count the number of charged particles in that part of the detector. And then we plot out the multiplicity. So at this end of the plot, we have many, many particles being produced. These are central collisions, they're head on. Then we get to a part of the plot where there are less particles being produced. This is a peripheral collision, it's more offset. There are less participants in my collision. And then all the way on this side of the plot, I have the ultraperipheral collision. So this is more of a glancing interaction. There's not actually any overlap that is happening. So if I come back here to looking at this net proton yield as a function of centrality, over on this side of my plot, I have the most central collisions, and then I have the most peripheral collisions on this side. We can see that baryon stopping decreases as a function of centrality, and it makes sense. Less stuff happening in my collision, less stopping. What we didn't expect to see was this scaling behavior. So this exponential that we fit for all of these different centralities, this exponential is about 0.6 or negative 0.6. And that's for a wide range of collision energies. If the quarks were the thing that carried the baryon number, we would expect this to change with centrality, because at more central collisions, you tend to have more collisions between your quarks. And there is a model that was able to reproduce this behavior, but they had to add in a baryon junction string-like mechanism in order to make this physics work. We can even look at this in Hyperon production. So here we're looking at heavier versions of baryons in lambda, Xi, and omega. This was a big effort of combining a bunch of different star results in order to make this plot. And so you can see this, there is still this clear exponential dependence, even for these heavier baryons. There is a caveat that we need to correct for the fact that strange quarks are harder to produce than up and down quarks once you get down to lower collision energies. Here we're at 7 GeV, and so we have to do a correction. I've linked to a talk that actually goes through the details of that. I'm just going to move on. So from the perspective of the baryon junction, the argument for why that it's a good candidate for baryon stopping is the fact that it's just moving much more slowly. So in my cartoon here, I have two protons that are colliding. The valence quarks are carrying about 1/3 of that proton's momentum. They're moving relatively quickly. They have been flattened into these little pancakes, versus the baryon number is much more spread out. It's at much lower momentum, and therefore has a lot more time to interact with the target and be stopped. I'm presenting in this talk 3 different methods of looking at these different baryon carriers. So one is the beam energy dependence of net baryon yields. We already went through all of those, good for us. The next 2 I'm going to be talking about is baryon stopping versus electric charge stopping. And then I will be talking about baryon stopping in photonuclear collisions. So we'll start with the charge stopping versus baryon stopping. We're not disputing the existence of valence quarks. We're not disputing their importance. They do, in fact, carry the charge of all of our baryons. And so if they also carry the baryon number, we would expect to be able to measure some sort of baryon number transport or baryon stopping versus charge stopping and get the same value if it's being carried by the same objects. It's one thing to say that, it's another thing to actually measure it. There's a reason that I showed you a bunch of baryon stopping plots before and not charge stopping. So for looking at net baryon yield, we can get a pretty good idea of what's happening just by measuring the net proton yield. If we're doing things properly, we would also measure the net neutron yield. But for the net charge or the charge stopping, we have to measure 6 different particles. These, if you've done any particle identification, you'll know these 6 different particles behave very differently in our detector. We expect this number to be very small, and different behavior means more corrections means more systematics. This is not a viable measurement to just do directly. Luckily, in 2018, STAR took what we call our isobar data set. So this was looking at ruthenium and zirconium collisions. These are isobars, meaning that they have the same number of total protons and neutrons, 96, but they have a different number of protons, so they have a different charge. So this data set is specifically designed to study how electromagnetism affects heavy ion collisions. And we did special things like making sure that the data set is really large, changing between collision species every couple of hours, making sure that the luminosity was level. This is a data set that is specifically designed to construct double ratios very precisely. And so instead of measuring the net charge, I can look at the net charge difference between ruthenium and zirconium. So that is the same formula I showed before. And then that can be related to these double ratios with some clever math. I have a backup slide if you want to go through it. And then for the baryon stopping, we're going to do it properly and actually measure the net neutrons. STAR can't measure neutrons. If we, at mid-rapidity, if we could measure neutrons, we wouldn't be able to tell the neutron versus the anti-neutron. And so instead, we're making we're using a thermal model approximation to instead estimate this by looking at the ratio of deuterons. This is something that is definitely true for primordial protons that are made in the initial collision. You have to be a little bit careful when you take into account feed down. That's something that was not taken into account in the results that I'm showing today, but will be taken into account by the time we publish. These particle yields were measured with the STAR experiment. We just found out today that the basketball team for the STAR experiment won the BNL tournament. So really cool experiment. In addition to that, we also have really good particle identification. So this is with a combination of what we call the time projection chamber and the time of flight detector. So the time projection chamber projects how charged particles travel in time. It also has this interesting property of ionization energy loss. So it's a charged gas. These charged particles, as they travel, they lose energy in a way that we understand and depends on the particle's mass. And so we can use it as a way of identifying particles. One thing, though, you'll note, these curves very well separated at low momentum. At higher momentum, they all run into each other. And so that is why STAR has an additional PID detector that is the time of flight. So that gives us a time. If we know the particle's momentum and the distance at which it traveled, we can then just convert that into the particle's mass. And so you can see we're able to separate the pi kp and also deuteron all the way to higher momentum. So again, we're measuring the the difference in the net charge yield between ruthenium and zirconium. We need the particle yields. We also need these double ratios. And then we're also measuring the net baryon yields using both protons and deuterons. And I want to emphasize that these are inclusive. We're not removing any of the contributions from heavier, weak decays. We want that to be included in our measurement. So here are the double ratios in all of their glory. And here are the particle yields. And then we plug them all into our formulas. So in order to plot these different values, we've constructed yet another ratio. Here we're looking at the net baryon yield and then dividing that by this difference in the net charge yield. We then scale by the difference in the number of protons, 4, and then divide by the total number of nucleons, which is 96. This ratio is constructed so if quarks carry the baryon number and charge stopping is the same as baryon stopping, we would expect this ratio to be 1. If the baryon number was instead carried by the junction, we'd expect to see more baryon stopping, and we'd expect this number to be greater than 1. You'll note that I've labeled this as a naive expectation. And so we instead need to investigate this in our model calculations. And we looked at a lot of models. We're going to start with this blue band, which is a calculation from Trento. So this looks at the effect of nuclear geometry. So in nuclei that have an excess of neutrons, they tend to have what is unfortunately referred to as the neutron skin. It is where the excess of neutrons tends to gather on the outside of the nucleus. And so that's something that's going to affect when we look at central collisions over here versus peripheral collisions, because I have the edges of that nuclei that are having a bigger impact. And we would expect to see this delta Q be smaller just because zirconium has a thicker skin than ruthenium. So then we looked at a bunch of different proton-proton simulations. So both Herwig and Pythia out of the box tell us that this ratio should actually be less than 1. I can sort of intuitively think of it as if I want to do charge stopping, I only need to move maybe 1 or 2 quarks all the way to mid-rapidity perpendicular to the beamline, versus if I want to do baryon stopping, I've got to get all 3 of my quarks all the way over there. And then Pythia also has this mechanism called color reconnection that you can decide to turn on. So this is sort of a gluon junction. They call it a baryon junction. It's kind of related to what we're talking about. And it's supposed to enhance the mid-rapidity baryon production. You can see it's doing its job. It increased this orange triangle to the green triangle at 1. And then we can also study what our models say should actually happen in heavy ion collisions. So here we're looking at a URQMD simulation, very comfortably under 1 for all centralities. We also looked at it in AMPT, which is yet another heavy ion simulation. This is one that actually has flow written into it. So again, it predicts that these ratios should be less than 1. Harder to get all 3 of my quarks all the way to mid-rapidity. AMPT interestingly showed that there should be more anti-strange quarks traveling to mid-rapidity versus strange quarks. We're sort of hanging out with our valence quarks at higher rapidity, sort of indicating that there's maybe some mechanism going on in that model that would allow for there to be more charge stopping than baryon stopping. And then, because in a simulation, you don't have to worry about all your efficiencies canceling out, we could then also directly measure the absolute charge transport instead of doing this difference. And we also see that it predicts that that ratio, if we were able to measure it, would be less than 1. We also used URQMD to validate our claim that if the valence quarks carry the baryon number, you would expect to see the same amount of charge stopping as baryon stopping. So here we looked at oxygen, aluminum, copper, zirconium, ruthenium, gold, and uranium. And you can see very clear correlation. Here we're scaling for Z, the number of protons divided by A, the total number of neutrons. And then if you take these same points and then divide by the baryon stopping, so this is sort of the inverse of the ratio that we were looking at beforehand, you can see that it starts to veer to 1, like our naive prediction would expect. So this is the reverse of the curve that we were looking at before. For our largest systems, so that's the most central collisions for our largest nuclei, we would expect in URQMD that this ratio would go to 1. So again, just to remind you what our plot looked like, we looked at all of these different simulations. They all say that this ratio should be 1, less than 1. Our data, however, very clearly shows that this is greater than 1. This is consistent with a baryon junction prediction, and that's just because those junctions travel so much more slowly within my nucleon, so they're a lot easier to stop. So baryon number enhancement, whatever phrase you want to talk about. And then you can also see that we have this same shape as our model that looked at the how the this says nuclear skin. It's supposed to say neutron skin. Oh no. I've shown this slide in a lot of places. So the neutron, so it tells us what the effect of the neutron skin should be. And you can see that we have the same relative shape. So that was baryon stopping versus charge stopping. I'm going to pause. If you have any burning questions on this measurement, now would be a good time.
I'm sorry. Could you maybe explain a little bit why the junctions carry a much small, it's a momentum fraction, never mind. Okay.
Yeah, so it's
Sorry, I was just thinking momentum then.
yeah. So yeah, it's just in the definition. So by definition, these are very low momentum gluons. I think in the original paper, it's an infinite number of momentum zero gluons,
Okay.
but that sounds ridiculous.
Yeah.
I don't say that. So we're all good for now. So we also have a separate measurement looking at photonuclear collisions. So this is where this photon fluctuates into a quark-antiquark pair and then interacts with my nuclei. It's kind of similar to an EA collision that we will be measuring at the EIC. The kinematics are a little bit different. These photons are quasi-real, and it can be used to study baryon stopping. It is in particular sensitive to this junction mechanism because it probes the nucleon at really low X. And it is also an asymmetric collision. So I know, so if these two gold nuclei were colliding with each other, I could have a junction coming from both sides. I wouldn't know what side my target was on. This is asymmetric, target is on that side. So these photonuclear interactions are a ultraperipheral collision. So that's those nuclei that are not actually colliding, they're sort of passing by each other in the night. Heavy ions are highly charged objects. When we accelerate them too close to the speed of light, they create these massive electromagnetic fields, some of the largest magnetic fields that exist in the universe. And the electric field becomes highly Lorentz contracted, and it becomes almost perpendicular to the magnetic fields. And using what is called the equivalent photon approximation, you can approximate this as a large flux of quasi-real or real photons. And these photonuclear interactions will happen through either the direct process where the photon interacts directly with the nucleon, or in the vast majority of cases, it actually happens through this resolved process that I showed before. So this photon fluctuates into this quark-antiquark meson colored dipole-like state, which then interacts with my nucleus. So this is an inclusive photonuclear measurement, meaning that we're not just looking for only a J-psi or only some type of particle. I'm looking for my photonuclear to hadrons in general. This type of process has become, gets more popular. One of the first big measurements came from Atlas. So they were able to isolate these events by looking in the photon going direction. They have their ZDC, their forward neutron detector. They looked for no neutrons going in that direction, multiple neutrons going in the other direction, and then they were able to select on the collision geometry. You can see from this event display that there are a lot less particles going in the photon direction versus the, in this case, lead going direction. And so they were able to select for that. They have an interesting and exciting measurement. It's been making the rounds. This is a two-particle correlation. So this is a way of probing the correlations in the initial state, no quark gluon plasma, probably. They were able to, they saw this funny shape in the V2, which they were able to relate to a color glass condensate. So talking about low momentum gluons, gluon saturation, a lot of fun stuff. I show this just to show photonuclear collisions important, good at measuring low momentum gluons. From the perspective of the baryon junction, again, this photon is fluctuating into a quark-antiquark pair, which would have a lot of trouble interacting with all three of the valence quarks at once, but is very good at probing the nucleon at low X. And so it can pull this junction out to mid-rapidity, and then you get sort of this spray of mesons in between. So it's an asymmetric collision. I only have my target on one side. And there's this prediction from the that comes from the mid-90s that we would expect an exponential dependence of about 1/2. Or yes. Yes, okay. So we've been talking about this junction stuff a lot in the last few years. And so we were able to convince that same theory group to do another prediction, looking specifically at deep inelastic scattering, or SIDIS. So this is an electron interacting with the protons. We have a virtual photon here. A photon has mass. It then produces some hadron. And so they specifically looked into the different possible processes. So you could have your junction come over to mid-rapidity and it pulled 2 of the valence quarks with it, 1 of the valence quarks with it, none of the valence quarks with it. And they looked at all of these processes individually. These all have their different rapidity dependence that's expected. And they concluded, as luckily we had been saying for a while, that this is the dominant process. They re-verified that. So again, you would expect the exponential dependence to be about y divided by 2. Also, because the junction is being pulled out without any of the valence quarks, we would expect this process to be flavor blind. So I could just as easily have a proton as I could have an omega, as I could have any type of baryon, because none of the quarks are actually being transported out. And they also expected, because I have a junction coming out without any of its quarks, I have all of these like loose fragmenting strings, that there would be a large multiplicity of mesons that are produced in this type of collision. So how do we actually measure these particles or this process at star? So here we're looking at a simulation from Beagle. So it's an EA simulation. We limited the kinematics to reproduce sort of what a photonuclear collision looks like. So in the photon going direction, we require that there is 1 neutron. In the gold, in this case, going direction, we require that there are multiple neutrons. And then we also do a similar sort of rapidity gap technique, as I talked about before, looking at the geometry of my collision and the spread out of particles. We don't quite have the detector acceptance of Atlas. So instead, we look at these forward detectors. We require that there's no activity in the photon going direction and a lot of activity in the gold going direction. We're using data that was taken in 2017. It has a collision energy of about 50 GeV, which is lower than your typical RIC 200 GeV. We use this data set because we were stuck with it. At the beginning, this was the only data set where measuring this type of process was possible. Previously, STAR's trigger required there to be symmetry in the detector in order to record its minimum bias trigger, which completely kills our signal. In future data taking, that's now not the case. So there will be hopefully a lot more measurements of photonuclear. But one of the good things that we realized from our simulation is actually at this particular collision energy, all of this fragmenting stuff of protons and neutrons hits our detector really cleanly. And so we can use this selection confidently. At higher collision energies, these protons and neutrons are at higher rapidity, and so they don't hit the detector quite as well. So people are currently working on how to isolate those photonuclear collisions at higher energy. So we do all of these cuts. Within our central detector, our simulations tell us that we should see this asymmetric distribution of more particles in the gold going direction. And that is what we see. So in this blue curve, these are the photons traveling in the east direction. That is east on the east side of star. Yes, star puts east on the left side of box. Since I worked on this, maps are now more confusing than they were before. But the photon is traveling in this direction, and I see more tracks on the other side of my detector. And in this red curve, the photon is traveling in the opposite direction. and I see more tracks on the gold going direction. So good so far. We can also look at the multiplicity of these collisions. So on average, they have a multiplicity of about 7 tracks, which for heavy ion collisions, even at RIC, is not that many. For a ultraperipheral collision, that's a lot. And so we know that we are biased for higher multiplicity collisions just because our detector is designed to measure particles. And so then we can also use as a baseline, we can also measure we can also measure our the same particles in peripheral collisions to gain more confidence in our analysis procedure, and also as a way of estimating the behavior of the peripheral background. So here I'm showing a double ratio, another one. Here we're looking at antiparticle to particle. So the orange points are the pi minus to pi plus in photonuclear collisions divided by the same ratio in our peripheral AA collisions. You can see that the pion and kaon is flat with 1 for all PT, where we have this very clear dropping at lower PT. So this is a soft baryon stopping possibly happening, double ratio, difficult to tell what's happening. The next step was to actually look at these spectra. So here is for photonuclear collision. We correct for the contamination of peripheral collision, peripheral hadronic events within our photonuclear sample. We estimate conservatively that contribution is about 10%, and then subtract off the behavior of that background using that peripheral AA data set that we talked about before. So then we can extract the yields. Here is a yield as a function of rapidity. So in blue, those are the antiprotons. You can see that they're flat. We interpret that as a combination of 2 different effects. One, the gold is going towards forward rapidity, so we know we have more tracks on that side. And then we also, based off of different models, expect that the proton-antiproton production, so all of my antiprotons are coming from this proton-antiproton production, that should have the opposite trend as baryon stopping. So those 2 effects cancel out, we get a flat slope. The green and red points you can see have a very clear forward positive slope. It's very good that this is an asymmetric collision, and I can measure that slope as going in one direction. If it was symmetric and I was trying to measure a bump, these error bars are huge, a lot less convincing. So that positive slope could possibly be due to this junction mechanism. We extract an exponential slope of about 1. And then I've also plotted it with that 0.6 that we were talking about before. That's that yellowish one that sort of collides with our data. And then we can also look at what Pythia in an EP collision says the slope should be. And that's that orange point that does not intersect with our data very much at all. I can summarize all of these different slopes into a lovely plot that took a really long time to figure out the plot. Luckily, it was not me who had to work on it. We have the junction Pomeron interaction. So Pomeron being soft gluons within my nuclei. So that's that 0.5 I've been talking about at the top. We also have a junction-junction interaction that should give us an exponential slope of about 1. Then we have our gamma P simulation. So this does not have a junction mechanism. Color recombination, loosely referred to as a junction, but kind of a different thing. Pythia slopes are really large. They show that there should be less baryon stopping than what we actually measure. We've got our slope of about 1, which I showed. And then we have different models looking in proton-proton. So Herwig and Box don't really agree with each other. But they have a slope that's a little bit larger than what we actually measure in data very consistently to be about 0.6. I turn on that color recombination in Pythia and it agrees with our data better. So yes, and then these junction Pomeron interactions are loosely consistent with our data. I would say that our data does not agree with Pythia out of the box. A look forward into the future, a lot of what nuclear physics is looking forward to is the electron-ion collider. I know many people in this room are very amped about it. A big part of the EIC is to understand how gluons behave within the nucleon, particularly gluons at lower momentum. When we talk about photonuclear collisions, a lot of times we talk about them as being pre-EIC, a sort of way of like figuring out what we want to measure, and they definitely are. I think that these talks to the importance of particle identification in your detector, particularly the importance of particle identification for a wide range of momenta. If we want to do this kind of measurements at the EIC, we're going to need to measure protons at very low momentum and design our detector to do so. But the kinematics are actually complementary. In electron proton or electron A, it's actually pretty hard to measure low Q squared, low virtuality of the photon, and at low X. That's because a lot of my kinematics are determined by the angle of my electron. And so for low Q squared, low X, I need to measure electrons very close to the beamline, very precisely, versus in ultraperipheral collisions, I get that for free. By definition, this is what is happening in my collision. So we're doing interesting physics right now. We're going to be doing interesting physics in the future, I guess. So to conclude, I showed a bunch of stuff as shown by my very dense summary slide. We talked about the net proton yield and how that scaled with centrality. We talked about baryon stopping versus charge stopping and how we measured that in our isobar collision data set. We then concluded with looking at photonuclear collisions and looking at the slope, the exponential dependence of my net proton yield. The slope is qualitatively comparable, possibly steeper to the slope in hadronic collisions. You can tell that that was a sentence that was approved for me to say publicly through many iterations. And all of these measurements, I would say, are not consistent with the baryon number being carried by the valence quarks and are consistent with this baryon junction, a Y-shaped configuration of very low momentum gluons, which carries the baryon number. Thank you so much for your attention.
Thanks, Nicole. That was great. Do we have questions?
I mean, this is a great talk. I like it, right? But I have a question about the way that we go about measuring the neutrons. I mean, I understand that this isn't something trivial. Then what I'm kind of skeptical about is the manner in which we're using the thermal model to calculate these two numbers here, because you rely heavily, of course, on our ability to measure deuterons and antideuterons in mid-rapidity, right? So I guess it's not necessarily a question, it's just a comment as to like whether or not we really do think this is a reliable way of doing this.
A lot of people, particularly on our paper review committee, had the exact same question and really took us to task on this particular squiggly line that I have here. So I don't have any of that to show you here because it's still internal, but it is something that will be discussed in the paper, probably in the supplemental material. But yeah, and that will be available soon. But yeah, that's something that we've thought about a lot, particularly in regards. This seems to be true according to our models for primordial protons. So protons produced initially in our collision. But then for heavier baryons, you need to be really careful when you're making this.
Yeah, this is true because but for me, knowing like what I guess FIST has in terms of the production of neutrons, there's a lot of decays from say like not heavy nuclei, but heavier nuclei, like lighter nuclei, like a bunch of these like weird helium states. that I don't really trust much, but I guess they do contribute to the bag and they do contribute to this. But I guess in principle, that just makes the errors
Yeah,
a little bit bigger.
yes, I'm sorry. What I should have said is this translates to more conservative systematic error.
There you go.
Yeah, I'd say, so at Rick collision energies, we're a little bit safer in terms of, we do get quite a bit of like lambdas at Rick collision energy, but even like omega is a harder particle to produce because it's heavier. So at the LHC, I think we'd have to be really careful in terms of this approximation. But yeah, I thank you for your comment and we are working on it.
Oh, me or?
None of your problem.
So you said that this current result still needs to take into account feed down effects and that the publication will. I'm just curious if you can speak on what direction, if any, this will shift the results this direction. Like, as I am having a hard time in my head, like picturing like how feed down affects the final ratio.
Really good if I remembered what direction it shifts. I think
Should we stop the recording?
it's ended up being a small effect.
Okay.
And if you look at the final plot, like it's a pretty dramatic result regardless. And I guess the phrase I am supposed to use is it did not affect the physics conclusions
Okay.
of our result.
Okay. Cool.
None yet.
Could you go to slide 37?
37, I can try.
No, I think just before this one, sorry. Could you walk me through this plot again? I'm sorry, I got lost.
I went through it really quickly. So this is sort of, I guess, like an intermediary stage. I debated whether or not to include this at all, but I heard people would say like, did you even think about pions and kaons? And yes, we did. So this is a double ratio, and that is because you do not have to correct for efficiencies when you do a double ratio. And so in particular, what's being plotted here is the antiparticle to particle ratio. It's pi minus divided by pi plus, k minus divided by k plus, p bar divided by p. And then we're looking at that ratio in our photonuclear collisions, divided by the peripheral AA. So this is a particular peripheral segment of my collision. It's 80% to 60%. Why didn't we do even more peripheral collisions? STAR doesn't do particle identification for more peripheral. We're not confident in the efficiencies of our detectors. So that was sort of what we're stuck with, but you can see that the multiplicity overlaps. This gives us confidence that the efficiencies will cancel out. And so the pion and kaon double ratios are flat and consistent with one. Nothing interesting happening here, hopefully. And then this proton double ratio has this very clear drop off at lower momentum. So that tells us that there is something going on with the protons. Turns out it was baryon stopping once we actually did the work of correcting for efficiencies. And then this plot also shows that it's really the low momentum protons where something interesting is happening. So it's a soft effect, which also sort of supports the baryon junction low X soft physics argument.
Thank you.
Yeah, so, great job, thanks. So I was wondering about, you kept this color reconnection kept coming up and you were like, it's kind of like the Baryon, but. So could you maybe elaborate a little bit more on that? Cause it seems like this color reconnection in Pythia comes up a lot where it's like, oh, and then we turn it on and things look a lot better. And yeah, I'm just curious if you had any like further thoughts.
My understanding is it is something that was put in specifically because Pythia could not reproduce baryon yields at mid-rapidity. And that's not Pythia's fault. A lot of models really struggle with that. And so it's particularly this mechanism. So it, I believe they used the phrase popcorn. I don't know what that means. But it's sort of like in the final state, so not in the initial state. In the final state, there's these junctions between gluons that form, and that enhance right before hadronization, and that allows them to, I guess, pull the quarks to mid-rapidity and sort of increase the baryon yields. We had a Pythia expert come to our workshop and we peppered him with so many questions. And one was like, is there a way that you could sort of have this like a mechanism in sort of like an initial state? Like, you know, we're drawing, we've got our little junction within our proton. Is there a way to put that? And the response was Pythia uses parton distribution functions. There's no junction parton distribution function. So right now it's not clear how to do that. Yeah, thanks.
So on one of the slides, you had the 7.7 all the way to 200, right? With slopes for gold. Yes. So it is 7.7 to 200. So you just combined everything between these energies?
Yeah, so this is the STAR data set that is referred to as beam energy scan 1. We're currently analyzing scan 2. So it had a bunch of different collision energies of gold from 7.7 because that's the lowest RIC can go to 200 GeV, which is our bread and butter collision energy. And so, yeah, so these are the inclusive net proton yields from 2 different STAR papers that I really should have somewhere on this slide.
So the reason I asked you this particular question is at 19.6, STAR shows, you know, weird proton, anti-proton distributions, right? So how that folds into all this information? Is it like too small of a effect to see or it just washed out or what?
Yes, I think it's too small of an effect to see.
Because if you look, I mean, you know, you are in the STAR. So like at 19.
I know of the paper, yes.
27, right? You have a different net proton ratio, well, with the just difference, right? But that should be reflected in these baryon junction, if that is true for sure.
Yes, I think that in order to see that jump in that paper, you needed to take a ratio. I don't remember what the ratio is. But here we're just looking at the net proton yields.
Squared over the mean. That's the jump you're talking about. It's not in the net proton number.
But I do agree with what I think is your overall point, which is the junction should, if it exists, it should be part of baryon creation. If we're seeing weird things in baryons, we should be able to explain that in the junction picture.
That's
Yeah.
exactly what, so that would be interesting to see the same thing with, you know, those 19.6, 27 GeV data set, you know.
Yeah, absolutely.
And another very stupid one is this. So if you go back to the comparison of URQMD to the baryon junction, do you also have another? Here you put, yeah, this one, no. Sorry. Yeah, exactly. This will do. So in Pameron picture, sure, you know, it can do magics, right? I mean, to get these ratios higher. But what your QMD has that you predict under, because naively, as you said, we would expect it to be one. Because you have protons and neutrons, they have all three baryons and all three quarks are charged. So what your QMD does to it, that it under predicts the ratio.
I think it's just the fact that for charge stopping, you don't need all of the quarks. So we're specifically measuring these ratios that we're looking at very mid-rapidity. So Y is in between 0.5, that's in the middle of our detector. So this would not be less than 1 if we were looking at the entire collision, but we're only looking at mid-rapidity. And so it is harder if you assume that the quarks carry the baryon number. To do baryon stopping, I would need all 3 of those quarks to get to perpendicular to the beamline. Versus for charge stopping, I only need 1 or 2 to move. That's my understanding. Also, you can see in this plot, at least in URQMD, we have an update of this AMPT curve, which is narrower. We ran more statistics. We, not me, someone who knows what they're doing did it. But you can see that there is sort of this centrality dependence. So you see that behavior of 4 more central collisions, which is on that side of the plot. There are more binary collisions happening between all the different quarks. And so we see that the ratio increases a bit and starts to go to 1. And you need to go to a much larger system in order to actually get it to 1, which is what we see here in that curve.
I'm sorry if this is a very naive question, but this is just something I have about how the models function when they model each of the valence quarks as having 1/3 of the baryon number. What does it output when it only scatters 2 to mid-rapidity? What does it mean for 2/3 of a baryon to be moving to mid-rapidity? Like, how does, because the final baryon has to be in integer numbers of baryons.
Right, so this would be that the baryons we're missing are small portion of the detector that we're looking at when they're at higher rapidities where we're not measuring. So 1 or 2 quarks moving to mid-rapidity means that we're getting mesons instead of baryons.
Okay, but then if baryon number completely is conserved, so like how does it pick if just in a sample there's only 3 quarks and 2 go this way, 1 goes this way?
So you also have more production of quarks that's happening through string breaking, I think is the word. So I have these like fields of these quarks that are moving further apart.
Yeah.
And then that turns into more quark-anti-quark pairs.
Yeah, so it can make quarks to complete the fraction of the baryon that's there, but I'm saying it can only like say a baryon went this way or it didn't, right? Like in the very end, once everything's condensed, like if you have 2/3 of a baryon going this way and the baryon and 1/3 going this way, how does that, I guess, solidify as 1 baryon here versus 0 baryons here, or like there's a
Yes.
Okay.
So yeah, these models are careful to conserve baryon number. And that's because baryon stopping is something that we've been studying for a really long time. Some of these models are not careful to conserve charge.
Okay.
Because we don't have a lot of data on charge stopping. And so getting this AMPT model to conserve charge was very non-trivial. So.
Thank you.
Can I have one very quick?
Yeah, sure.
So in one of the picture of bagel simulation you were showing, right? EA?
Yeah. Yeah.
Yeah, it's fine. It's fine. So it says TPC, but this is for you considered star configuration with the Beagle software? Or?
Yes.
I see. Okay.
Yeah. So yeah, Beagle is our only EA simulation that's available right now. And is currently a work in progress. So.
But you're not planning to use the star configuration for the EA?
No, there's going to be a completely new detector. Yes, star is 20+ years.
So, I mean, I was wondering what was the motivation for this?
We were trying to understand what the kinematics of our photonuclear collision should look like and what we should expect to see. So this sort of helped validate our particular data cuts that we were using. We don't have access to the full collision geometry. So instead we used these forward detectors. So that's the what we call the VPD and the BBC. And we were able to select on our event activity. So our simulation tells us that there should be nothing in these detectors, and then a lot of stuff on that side where the gold is traveling. And then from here, we predicted what the charged particle distribution should look like. And then we saw a similar thing in data, which made us more confident that we were doing the right thing.
Thanks, Nicole, and yeah, thanks again.